Dear colleagues, it is my pleasure to welcome Dennis Höning for this week's seminar on climate evolution of rocky planets and the impact of life. Dennis has done quite a bit of his career on the German Aerospace at the German Aerospace Center in Germany, but he is now at the Vrije Universiteit Amsterdam in the Netherlands. And he is co-leading one of our working groups at the European Astrobiology Institute. Maybe he wants then to say a couple of words about that after your talk, Dennis. But now I would like to go in medias res and leave the word to Dennis for his presentation. Welcome again, Dennis. Welcome to you all, and the floor is yours.
Thanks, Walt, very much. Also, thanks for attending. It's really great to have so many interested people, like 50 people here, so that's amazing. As Wolf already told, my name is Dennis Höning. I'm at the VU Amsterdam, and also I'm part of the Dutch Origin Center, which is an interdisciplinary community and initiative to study the evolution of planets and life. So today I'll tell you something about habitability of rocky planets. So we all are interested in habitable planets and in the question of, is there life somewhere in the universe? So one important aspect of it is the climate of rocky planets and how to model this. And the second part of the talk is about interactions between life and the planet. So when we talk about rocky planets, in our own solar system, it's clear these are the inner planets. So rocky planets in terms of solid surface. When we talk about extrasolar planets, planets are considered to be rocky if they have less than 2 times the Earth's radius. Otherwise, they would more be Neptune-like or Ganymede-like. When we talk about habitability, so habitability of a planet is often associated with the habitable zone, which you see here for the solar system and for the Kepler-22 system. So the habitable zone is defined as the distance of a planet from the star that allows for liquid water on the planetary surface. So we all know liquid water is one of the main requirements for life as we know it. So in order to have the right temperature on the surface of a planet, the planet needs to have, of course, the right distance from the star. The star has to have the right stellar luminosity. But also what is very important are greenhouse gases in the atmosphere of the planet, like CO2. And when you, for example, compare also planets in our solar system, like Earth and Venus, you see that most of the parameters are quite similar, like radius, mass. Also, the solar distance is not a huge difference there, but still you have a huge difference in the atmospheric CO2 partial pressure. And this, of course, leads to a very hot, uninhabitable surface of Venus in contrast to Earth. So where does this huge difference come from? So in the next 30 minutes, I'd like to start with general thoughts about the carbonate-silicate cycle, how to model it, and especially I will talk about which processes in the carbonate-silicate cycle must be considered on which time scales. Then I'll talk about the habitability of ocean worlds. So in ocean worlds, in this talk, I will not consider planets with a really huge water layer, but I consider planets which have the entire surface somehow covered with water. Then I'll talk about climate evolution of stagnant-lid planets, and finally I'll talk about the impact of life on the climate of a planet, and in particular on the stability of the climate. All right. So we start with the Earth's long-term carbonate silicate cycle. Most of you are familiar with it, I think. So we have CO2, which is dissolved in rainwater to form carbonic acid, and this dissolved silicate rocks and weathering products are washed into the ocean, forming calcium carbonate, which is then subducted into the mantle. And at high pressures and temperatures here, carbonates become unstable again, and CO2 is outgassed into the atmosphere. And the important thing here is that that the weathering, so that we have a negative feedback here, because when we have a very high surface temperature of a planet, this means we have a large weathering rate, and with the weathering, CO2 is removed from the atmosphere, which cools down the surface again. So we have a stabilizing feedback here. So when we want to model the carbonate silicate cycle, it is important to consider the time scale. So when you consider a time scale smaller than or shorter than 1 million years, then you can treat volcanic outgassing of carbon as an input parameter. And yeah, then you need to model ocean chemistry to know how much CO2 is dissolved in the ocean and remains in the atmosphere. And then you end up with CO2, and the CO2 determines then the weathering flux, the continental weathering flux and the seafloor weathering flux. And these fluxes are actually alkalinity fluxes, so bicarbonate, for example. And the alkalinity determines then how much carbon and alkalinity can be buried in the seafloor. So important here is that the CO2 determines the alkalinity source, and the alkalinity in turn determines the carbon sink. So when you consider now longer time scales than 1 million years, the alkalinity step can just be skipped. And basically we have CO2 dependent weathering by which CO2 is then buried. But if you consider this long-term carbonate silicate cycle like longer than 1 million years, 100 million years, even billion of years, then it's important to consider that all of these carbonates which are subducted are somehow in the plate and in the subducting plate. And this means that a part of the plate is directly degassed at the subduction zone, so with arc volcanism, where the rest of the carbon is transported further into the mantle. And the CO2 in the mantle determines how much carbon is degassed at mid-ocean ridges. Yeah, so this is the carbonate silicate cycle on longer time scales. And here is a crucial step. So to know how much CO2 is directly outgassed at volcanic arcs and how much is transported further into the mantle is a crucial step here. And this in turn depends on the temperature profile of the subduction zone. So you can imagine that when you have a subduction zone and when you have a very hot subduction zone with a large temperature gradient, then most of the carbonates will get unstable and be degassed, while when you have a cool subduction zone, most of the carbonates remain stable and can be subducted into the mantle. And the problem is that even on Earth, you have a huge range of temperature gradients of subduction zones. You have cool subduction zones, hot subduction zones. And so what you can do is to apply a stochastic model which relates the fraction of subduction zones with decarbonation to the mantle temperature. Because you can imagine that when you have a hot mantle, a hot surrounding of the plate, then you also will have a steeper temperature gradient in the subducting plate. And so this is what you can do here. And now let's come back to the question of the habitability of ocean worlds. So can actually planets with a surface covered by water be habitable? Or if you imagine this movie from 1995, can there be life on planets which are covered by water? So what do we need to do? For ocean worlds, we of course do not have continental weathering, so we only have seafloor weathering, which is a crucial difference here in the model. And for seafloor weathering, the problem is that the exact dependence of seafloor weathering is unclear. If it mainly depends on the CO2, if it depends on the temperature of the surface of the bottom ocean, or on the pH value of the ocean, it's not entirely clear. So there are arguments for a direct CO2 dependence of seafloor weathering, so that you have a weathering flux, plate speed, then the partial pressure of CO2, and with some exponent alpha. But there are also other arguments, for example, that you need to account for dissolution kinetics. So you have the seafloor weathering flux proportional to exponential function, and then you have some temperature of the bottom ocean, and you have a pH value here. And these are really two very different scalings. So if you have the temperature-dependent weathering form, you will have a very strong negative feedback, because everything which is temperature related with an exponential form gives you a very strong stabilizing negative feedback. And there is one word of caution also. If you consider planets with a very small degassing rate, then this function will not really work, because you end up with an atmosphere with a very low CO2 concentration, and then there is nothing which will really stop the CO2 from being removed from the atmosphere, because you do not reach 0 Kelvin here. So so for planets with really small degassing rates, this does not really work here. All right, let's see how the model looks like. So here I present some results of climate evolution of ocean worlds. So what you see here is CO2 partial pressure evolution and surface temperature evolution. And I compare a case with a CO2 dependent weathering function and a temperature dependent weathering function. And yeah, as you may expect, the temperature dependent weathering function ends up with a smaller CO2 partial pressure and surface temperature. And that is because temperature dependent weathering is a strong negative feedback. So you remain closer to the present day value, which is about 285 or 88 Kelvin. The next thing you see is that we start with different initial mantle temperatures in blue, yellow, and red. And that this initial mantle temperature is not really important. It's only important in the first billion year. And afterwards, the system approaches an equilibrium state. And finally, what you see here is that through the entire evolution, the surface temperature and the atmospheric CO2 decreases. And this is because the mantle cools down with time, which means that more and more subduction zones will get cool enough that to avoid decarbonation. So more and more carbonates can be subducted into the mantle. Also, the effect is not very big here. And of course, when you consider thermal evolution, it's not only the mantle temperature which decreases with time, like from 2000 Kelvin to 1600 Kelvin. It's also the stellar luminosity which increases with time. And if you consider now a trajectory where you model the planet evolution, so the planet cools down and at the same time the luminosity increases, you can imagine that your climate will more or less be stable for a longer period of time, and the surface temperature will not increase that strongly. Okay, to sum up the habitability of ocean worlds, first we expect ocean worlds to be around 40 Kelvin hotter than the Earth for the same irradiation. And the main uncertainty is the temperature dependence of seafloor weathering here. We also saw that the thermal state of the mantle plays a role. So mantle cooling can compensate for increasing solar luminosity, which enhances habitability. And what this means to the movie, I leave it up to you. All right, the next part I want to address is the habitability of stagnant-lid planets. So it's entirely unclear if plate tectonics occur on extrasolar planets. Even for the solar system, we see on Earth we have plate tectonics, on Venus probably not, on Mars certainly not, and it's unclear basically if what should be expected for extrasolar planets. If we don't have plate tectonics, this means that we don't have mid-ocean ridges, and which means we have a smaller degassing rate. But on the other hand, we have an insulating lid. And so this means that we have a smaller cooling rate of these planets. And finally, there is a question, if there is no subduction, does this also mean that there is no carbon recycling? Well, first of all, I tell for those who are not familiar with it, what is the difference between plate tectonics and stagnant-lid. So for plate tectonics planets, you have the lithosphere, which is part of the convecting mantle. And on the other hand, you have stagnant-lid planets where convection takes place beneath the stagnant lid. So when you don't have subduction, which you have on plate tectonic planets, you can still have some kind of carbon cycle. So you would still have volcanism, degassing, and by this volcanism, you will have basaltic crust production. And when you have fresh basaltic crust, this can be subject to weathering processes. So you can carbonate, so carbonates will form and be stored in the plate. And you can imagine that with time, when you have new volcanic eruptions, the carbonated crust can sink downwards. And this is the decarbonation depth here. So at some point, carbonates will become unstable again. But when you now consider later evolution and even later evolution, then you see that as soon as the decarbonation depth is reached, you not only have degassing from the mantle, you furthermore have degassing because of the decarbonation process here, and your weathering processes will be stronger. This means the concentration of carbonates in the crust will increase with time. And in the same time, the decarbonation depth moves downward. So, so now we can apply a decarbonation function dependent on so decarbonation function dependent on pressure and temperature, and then you can apply 1D thermal evolution model, and we apply a degassing model following a model for redox melting. And this is the result of it. So there, here again, I show the CO2 partial pressure evolution with time, the surface temperature evolution with time, and yeah, there are some things you see. So at first you see the temperature-dependent weathering function here at the bottom, and the CO2-dependent weathering function on the top. You see that when you take the temperature-dependent weathering function, all of your CO2 from the atmosphere will be removed after around 3 or 4 billion years. And this is simply because your decarbonation depth increases, and yeah, so your weathering processes will be larger than your degassing rate. And this is one problem for the temperature-dependent weathering function. So when you have CO2-dependent weathering, this problem is not really there, because your weathering will also decrease when your CO2 decreases. So the next thing you see is that when you start with different initial mantle temperatures, then this difference will lead to a different CO2 partial pressure, not only in the early evolution, but via the entire evolution. So when you, for example, consider or compare the blue scenario with the yellow scenario, there is 100 Kelvin difference in the initial mantle temperature. And the surface temperature can vary by almost 50 Kelvin in the end. So the initial mantle temperature is really important. This is, of course, because all the CO2 which is degassed at the beginning cannot be really recycled back into the mantle. And finally, what you see is that also here in the late evolution, your surface temperature decreases again because of the increasing decarbonation depths, which means that you remain your planet habitable for longer. And yeah, you can also vary the mantle oxidation state. So here you see the reference case of an oxygen fugacity of the iron with heat buffer. And here you see a more oxidized mantle. And you see that this really makes a huge difference. So for a more oxidized mantle, you can end up, especially when you start with a hot mantle, like in the blue scenario, you end up with like 100 bars of CO2, like Venus has. So this makes a big difference. Good. To sum up the habitability of stagnant-lid planets. So we saw carbon recycling is restricted to the crust in the atmosphere, and outgassed carbon from the mantle cannot really be recycled back. We saw that the initial mantle temperature determines the early outgassing, and this has an effect on the entire evolution also later on. And we saw that the mantle oxidation state substantially affects the atmospheric CO2. You can even reach Venus with this. And we saw atmospheric CO2 decreases after around 3 billion years, which can compensate for the increase of solar luminosity. All right, finally, the question, how does Earth's biosphere affect climate stability? Good. So is there an interplay between life and the climate of a planet? And having this question ultimately is related to the Gaia hypothesis by James Lovelock and Lynn Margulis. So in short term, the Gaia theory says life interacts with its environment in a way to form a self-regulating system that maintains habitable conditions. And last year in Exeter, there was a Lovelock conference in the honor of James Lovelock, of the 100th birthday of James Lovelock. So this is this guy here, and this is the organizer, Tim Lenton, and this is here a giant birthday cake for him. Yes, and in the background, that's me just staring at the birthday cake. However, this conference really inspired me of thinking more about the interaction between life and the planet. So, of course, when we are interested in climate stability and interactions on all timescales, we have to consider the more detailed carbon cycle model. So we have alkalinity production here by weathering. We have carbon degassing at mid-ocean ridges, for example, and we have an alkalinity and carbon sink below the sea level. And the first thing what life does to the planet is that it enhances weathering. So the alkalinity flux is enhanced if we have surface life on the planet. And there are different examples for it. For example, chemical effects, the production of acids by microbes, by fungi. You have also physical effects, for example, by roots of trees breaking rocks. So life is enhanced biologically. And since the biological productivity and therefore the weathering rate increases with temperature, you can remove more CO2 from the atmosphere, which establishes a negative feedback. And there are different models for biological productivity or the enhancement of weathering. So here are two different examples, the solid and the dashed line. And the black dot is the present-day Earth. So here you have the productivity dependent on temperature or an atmospheric CO2. And what all of these models have in common is that at the present day, you have an increase of productivity when you increase the temperature of the CO2. And this means that you have a negative feedback here. So if the temperature increases, productivity increases, and you remove more CO2 from the atmosphere. And this model has been applied several times. For example, here in the Lenton and von Blow paper in 2001, they modeled how they modeled how the Earth in a biotic scenario and in an abiotic scenario would evolve. So 0 is present day. Now we go into the future. Luminosity increases, and at some point, the biological case or the biological scenario reaches a threshold where life gets extinct, and you jump into the abiotic scenario here. So you suddenly increase the temperature. Another example is here the illustration by Chopra and Lineweaver. And so what they illustrated here is the habitable conditions on a planet, which do not change over the entire evolution. So these are the habitable conditions. And here are the actual planetary environments, which of course change with time because, for example, the luminosity increases. And then you here have the origin of life, and at some point you get out of the habitable zone or the habitable environment, and life get extinct, and you have a diverge evolution of the environment and the habitable conditions. But on the other hand, when now life can change its environment to keep it habitable, you see that that the planetary environment can remain for longer in the habitable condition, and this of course expands the lifetime of the biosphere. So biological enhancement of weathering is not the only thing where life influences the planet. So when you think of shallow water organisms like coral reefs or corals, for example, what they do is they take bicarbonate and produce calcium carbonate out of it. But what the important thing is that that calcification leads to a release of CO2 into the atmosphere. So what corals basically do is to produce CO2. And there is a negative feedback associated with this because the rate of calcification depends on the ocean saturation state. In other words, if you have more CO2 in the atmosphere, then the reaction of producing CO2 slows down, and also vice versa. When you decrease the CO2 of the atmosphere, the reaction speeds up, and in total you have a negative or stabilizing feedback because of shallow water organisms. You also have deep water precipitation, for example, by these guys here. So they precipitate calcium carbonate in the open ocean, and this sinks then downwards to the seafloor, and then in the shallow regions it can accumulate, where on the deeper regions it will dissolve. So the shallower regions are supersaturated, and the deeper regions are undersaturated. And interestingly, the depths, the calcite, so-called calcite compensation depths, which determines how much or where calcium carbonate can be accumulated, depends on the ocean saturation state. And there is also negative feedback associated with it. So if you have more CO2, the calcite compensation depth moves upwards, and more dissolution takes place. And by this process, CO2 is consumed, so you have a negative feedback here. All right, then we have, then we can model all these things. So we have biological enhanced weathering, we have shallow water organisms, and we have deep water organisms, calcite compensation depths here. We can model all these things, But to model climate stability, we need to add some oscillations to the model. And with this, we can use a simple model of mountain uplift and erosion, which just adds oscillations to the model. All right, and here you see how it then looks like. So what you see here is are these oscillations I was talking about. First, so in the surface temperature over time, first averaged over 100,000 years, so these are the thin lines, and then averaged over 1 million year, which are the thicker lines. And the different colors are the different scenarios which are modeled. So all of these scenarios have the same input flux, so the same perturbation force, but they respond differently to it. So the reference case is a system where we just ignore the calcification feedback. So here we set the barrier flux proportional to the weathering flux. Then we have a scenario in blue with marine organisms. We have in yellow a scenario with biological enhancement of weathering. And we have in green a scenario which combines all of these biological processes. And there are interesting things you can see. So one thing is when you are looking at short periods, like averaged over 100,000 years, you see that the amplitudes of the red and the yellow curve are much higher than for the green and the blue curve. So this means that the blue curves, where marine organisms are in the system, like blue and green, are much more efficient in damping these oscillations than biological enhancement of weathering. But when you now look at average over 1 million years, you see it the other way around. So in these time scales, the biological enhancement of weathering is much more effective in reducing the oscillations and keeping the climate stable over these periods. So what you can now do, if you have a long time series, you can do a frequency analysis and plot the amplitude of the spectrum over the frequency. So here you have low frequent oscillations, so large periods, and here you have high frequent oscillations. And you see that the red line, so the reference case, has almost the highest amplitudes throughout the entire spectrum, where the green line, which is the biotic case, has a much lower amplitudes over almost the entire spectrum. And what you also see, what you already expected probably, is that when you are looking at low frequency oscillations, so long wavelengths, the biological enhancement of weathering is much more effective in stabilizing the climate, while on long frequencies, so short periods, which are the thin lines, the marine organisms are much more effective in stabilizing the climate. The transition is here more or less at 1 million year. But there is also one disclaimer, because the reference case is not always necessarily representative of an abiotic ocean, because an abiotic ocean is also a very complex system where at some point precipitation will take place at a very high pH. And depending on the saturation threshold for inorganic precipitation, a high pH value of abiotic oceans may also damp high frequency oscillations, which means that the red curve will also be lower here at very high frequencies. All right, to sum up the third part, marine calcification feedback damps climate oscillations smaller than 1 million year while keeping the ocean pH low. And we saw biological enhancement of weathering helps stabilizing the climate on timescales larger than 1 million year. And overall, we can argue that life plays an important role in stabilizing the climate on timescales starting from some 100,000 kiloyears. Good. Take-home messages, if this is the right phrase for the current situation. Yeah, we need to better understand the tectonic and geological state of exoplanets in order to assess their habitability. We saw that it makes a difference if you have water-covered planets, if you have stagnant-lid planets, for example. But still, the good news is both planets, stagnant-lid planets and ocean worlds, can be habitable over a long period of time, and mantle cooling even helps to extend the habitability. On Earth, we saw life helps to stabilize the climate and thereby to keep it habitable. And we can ask the question, would inhabited exoplanets also remain habitable for a long period of time? Yeah, with this, I want to close and thank you very much for your attention. Thanks.
Thanks a lot, Dennis, for this very nice presentation. We open now the discussion. And if we want to ask a question or make a comment, please just put on your video screen, switch on the camera, and maybe wave your hands or something like that, that I can see that you are wanting to ask a question.
Hey, Dennis, can you hear me?
A bit.
Yes, you're a little bit garbled, but I mean, it seems okay.
Yeah. Can I have a quick question? It's very nice talk. So
thank you.
I'm wondering why the carbon, like whether the carbonate on the stagnant-lid planets can't be recycled into the mantle.
Almost not. So sorry. Maybe I can come back to this slide. So as you see, we have a decarbonation depth here, and this is basically the depth where the majority of carbonates will become unstable. Because you can imagine, for a stagnant-lid planet, you have the temperature gradient in the stagnant-lid is much higher than for a plate tectonic planet. So for a plate tectonics planet, you have very cool subduction zones. So subduction zones which very efficiently transport carbonates into the mantle. But this is not the case for stagnant-lid planets. So the gradient here is much steeper. And this means that most of the carbonates will get unstable here. So this is why the recycling is more or less restricted to the atmosphere and crust. But depending on the mineralogy, some of the carbonates will probably, some phases will probably remain stable. But I would say that it's very limited.
Yes, next question, please.
May I ask you?
Antonello.
Yeah, thanks. First, thanks a lot for the very beautiful presentation. Very, very interesting. One question. Typically, we say that one of the conditions for the habitability is the fact there is a plate tectonics in order to have recycling of the CO2. While this seems to be a bit obsolete now, because you have shown that even water worlds, ocean covered worlds, or planets without plate tectonics, but just the other mode of convection can host life anyway. I mean, habitability. So it seems, in a sense, it's an interesting result because it shows that this point of departure is not so much needed, right?
Yeah, you're correct. I also agree. So yeah, we should be open-minded when thinking about habitable planets. But of course, it is still crucial to know if there is plate tectonics or not, because it affects somehow the habitable zone of these planets.
Right. Thank you. Thank you very much.
Thanks.
Any more questions, please? You can also type in your questions into the chat if you want.
I have, well, first of all, thanks for so exciting talk and very nice, motivating a lot.
Thank you.
So I have, Dennis, one question. Perhaps it's a more exotic one. As you know, as we are also talking about exoplanets, and we have all this evidence for giant planets nearby the stars. Just following the different models and people, for example, it comes to my mind the models by Helmut Lammer, suggesting that perhaps some terrestrial planets at the very beginning retain a significant amount of hydrogen, and then it evolved towards the terrestrial planets we know. What do you think about this theory? It is more curiosity in this case. Thanks.
Yeah, I mean, I'm a fan of Helmut Lammer's models, so I think that's an important thing to consider. So what my models consider is so-called secondary atmosphere. So we assume that all the primary atmosphere, due to the accretion, is somehow either escaped to space at some point of time or subducted into the mantle, and then by interior processes, so volcanism, a secondary atmosphere of CO2, for example, is built up. So these models can only consider geophysical processes which are responsible for the secondary atmosphere, not for the primary atmosphere.
Okay, thank you.
Talk, there's a question coming into the chat. I read it out. By Giuseppe Marante. I understood that, however, the negative feedback provided by plate tectonics is stronger. It means more effective. Am I correct?
Yes, that's correct. Yeah, so especially on long-term time scales, plate tectonics really allows to have the mantle playing a role, and for the mantle to be part of a regulating mechanism, which you don't have on stagnant-lid planets. So it's restricted. That's correct.
There was a follow-up question also. Could these models be used intensively to determine the extent of the habitable zone?
I mean, varying the characteristic of the exoplanet, of course.
Yes, this could be an interesting application. Yes, I agree. Of course, it depends on many more parameters, especially the composition of a planet, which needs to be taken into account. We already saw that the oxygen fugacity plays a role, but also, for example, the mean density of the planet, which determines the relative core size and therefore also the amount of carbon in the mantle, but also, for example, the strength of convection, because in a thicker mantle you have a stronger convection, for example. So all these things have to be considered if you talk about habitable zones. But in principle, I think yes, these models can also be applied.
This is interesting because we performed a similar exploration of the parameter space with a kind of a EBM for the climate of rocky planet, and there what we varied were the characteristic of atmosphere and of the geography of the planet. Just doing an intensive exploration of parameter space to determine the extent of the habitable zone. I think these models could be used the same way.
Yeah, that's very interesting. I agree. So I mean, in terms of climate models, these models I showed today are very simplistic. They are basically 0D models. So yeah, probably a combination of these models would be very interesting.
Dennis,
thanks a lot.
You talked briefly about the ocean worlds, and you mentioned the pH and the CO2 concentration in the water according with the life of microorganisms and so on. So I remember a couple of slides during your presentation. Do you have any more comments about these arguments? Because I mean, just for example, if we consider the phytoplankton as one of the microorganisms that may be interesting for us because of the production for dimethyl sulfide, for instance, is maybe one of the biosignature interesting in these fields. But what maybe happens according with the pH range and the CO2 concentration? Do you have any news about that?
Good question. I think I didn't understand everything of this question.
The question is if I have an ocean and you talk about the pH of the water probably and the CO2 concentration in the water, and if we consider the phytoplankton, for instance, the life of this microorganism is constrained in the value of the chemical parameters of the environment. A couple of them may be the CO2 and pH, right? So it's maybe different from the Earth, but what's your comment, or do you have many more comments about this arguments?
So you mean present-day Earth organisms, if they can adapt to this situation of CO2 and pH, or?
Right. Right.
Yeah. So I'm not a biologist, so I do not really know the extreme conditions where these organisms can survive. I'm sure there are many experts, probably also in this room, who have better ideas about this. So what I only do is to take general production rates of calcium carbonate from temperature, from CO2 and chemistry.
Okay. Thank you, Dennis.
Okay, I don't. There is another question. Well, we have to. There is, yeah.
Can I have another question? I'm sorry. It's very nice talk again. So, the question is have you considered the state of water on the planet surface when you simulate the carbon weathering? Because I mean, for the stagnant-lid planets, you showed, at the later evolution stage, the surface temperature may reach like about 100 Celsius degrees C, which may evaporate the whole ocean, and then there's no enough liquid water for water rock interaction.
That's of course a very interesting question, and yes, we did not account for it, and it's also particularly so we assume that we always have some water left for interactions of rock, but it's also a very interesting question because we did not consider the deep water cycle in these models, which should then also be considered, because even if you have a constant budget of water, it will somehow be distributed between the surface and the mantle. So to get clues on how much water is left on the surface, you should not only consider escape processes, evaporation, and so on. You should also consider the equilibrium between the mantle and the surface. This is another complication step, of course, but yeah, would be interesting to look at.
Yeah, great, thanks.
So then there is a final question. We have to conclude then afterwards, I think, by Josep Trigo Rodriguez. I wonder how much influence could the extensive presence or absence of liquid water have in the upper mantle of your model?
Yeah, I mean, yeah, this goes basically in the same direction as the question before. So in this model, we did not account for the water cycle. I did water cycle models in the past, and indeed it can play an important role because water lowers the viscosity in the mantle. So this means if you have a wet mantle, you have rapid mantle convection, which also has an effect on the speed of the subducting plates. And then you can make the model more complicated. For example, if you have a faster subduction rate, then the carbonates will remain stable for a longer period of time because the subduction zones are not heated up as efficiently. Yeah, so the amount of water in the mantle is indeed something which should be included in future models, and also coupling the water cycle to the carbon cycle in the sense. This would be interesting.
Okay, that now concludes our seminar. Please come again in 2 weeks when there will be Ina Catalina Plaza talking, and we will have the seminars hopefully with a little bit of a Christmas break on a bi-weekly basis from now on, at least until the 23rd, but we want to continue until summer with those. Thanks a lot for coming. Thanks for Dennis for giving this talk on a bit of a shorter notice, and see you then in 2 weeks.
Thank you. Bye-bye.